Okay, hi guys, welcome to part two of the lectures. Thank you for watching the last one. Let's just get right to it. We are now talking about the processor. So the processor is normally used when buying computers. You'll hear the person looking for a Core i5, Dell or HP or Mac. I'm looking for a Core i5 or a Core i7 or Core i3. Those are the those are the processing units within the computer that allows the computer to run to do certain instructions. Depending on how good the processor is, how many instructions can it execute within seconds, and how complex can it handle instructions. So we're going to get to that. It's typically called the CPU, abbreviated for Central Processing Unit. Uh, it follows program instructions, and by that I mean that every program has a set of instructions. It's either I'm taking a picture, uh, I'm putting in some letters so that they can be outputted as something I see on the screen. Those are instructions. So the CPU follows program instructions. That's what I mean. Typical capabilities of a CPU include: it adds, it subtracts, it multiplies, it divides, move data from one location to another location, e.g. from a flash drive, from the computer to a flash drive, from a flash drive to the computer. It can divide. You've seen it. You've seen a computer. And for those who have not touched a computer yet, this is what a computer can do. Uh, a computer software has an operating system, uh, a system in which it operates from. So either Windows 10 is a platform that it creates an environment in which certain programs can work. You'll hear that this one is not compatible with Windows. It's only for Mac, or this one is for Mac only. It's vice versa. So the operating system allows us to communicate with the computer to do the task that we want to do. It is a program, but like I mentioned earlier, it's not an editable program, it's a system program. Allocates the computer's resources. It allocates the for you to be able to access the USB, for you to be able, and not like ask for the USB and then the computer switches off. It allows you to, it allocates, it says, okay, go there, go there, go there. And that's why it's so important when buying a computer. It responds to users' request to run other programs. So let's say a program like print, Microsoft Word will communicate. Microsoft Word on its own is a program. It communicates with another program called print, and those programs communicate, and then there's an output. So that's your request. You wanted to print, but you do not realize that there is a communication within programs that allows you to have this response from a computer. So the there are many different types of computer operating systems. I've mentioned them above. There's Unix, which is user interface. There's Linux. There's DOS. There's VMS, which are virtual machines. There's Macintosh. There's Windows. Yes, and the list goes on. Ubuntu. Yeah. So a computer, we've identified, consists of a program. Many programs interacting with each other, but they are programs. And some data which is inputted and processed into information. Okay, and then now these programs have different levels of languages. There's high level languages, which include your Java. I'm sure you've heard about it. There's the C++, which is what we're doing now. There's C Sharp, which is a more recent language. And there's Visual Basic, there's Python. All of these languages are languages that the computer can understand. They are created so that the computer can process that information. We use English, but we can't give a computer English. These days, there are programs that are almost getting there, but they are not really there, like do this, but you'd have to write a long essay to make it do something simple. So the programming language is there for that. It executes with simplicity of syntax, something that the computer can be able to use and create output without needing a long statement. And then these high level languages resemble one, human languages, are designed to be easy to read and write, use more complicated instructions than the CPU can follow. By that we mean that a source code is really complicated when you're just looking at it. So the CPU sometimes needs a compiler, something that will translate that so that it can be read into a machine language. That machine language will translate it to an object language, and then you will see tasks being done. So the high-level languages like your Java and all of that will be translated into something that's easier for the computer to understand and then output. But the whole processing is done, yeah, by the computer. Must be translated to zeros and ones for the CPU to execute the program. So the machine language that I'm referring to is this. It's binary, it's ones and zeros. I'm sure you've watched the movie The Matrix, and here in the back you'll see 1, 0, and they are in green and they are going all around. That's coding. That whole movie is about coding. If you really are fanatic like that, you would be able to identify that. And then we move on to low-level languages. An assembly language like add X, Y, Z is simple. It just means add X, Y, and Z, right? But the programming language needs to translate that into machine language. And add could mean 0110. It's not add. It's not going to be written in English. You see, I'll get into more detail as we go so that you can understand. For now, just understand that there's a language that you understand as a person who's speaking English, who was taught English. So you know that in English you don't say, like from Sepedi you would say ke kgopela, but in English you know that the term you would use for you to be understood as an English person, you would need to ask, may I please? You get what I'm saying? So that's just the same way. You're learning a language of machines. So when I mean machine language, I mean just that. You're learning a language that the machine is able to understand and communicate with. The CPU can understand that. Compilers are things that translate something from a very complex code into a machine language. They are there inside. You can't see them and all of that. Source code is the original program in a high-level language, like using your C#, your Java, your C++, which is what we're doing now. And then object code is the translated version in machine language. I hope you understand me. I hope I'm not too fast, so we are going together. What's the difference between a source code and object code? That's homework, based on the way I've explained now. What is the difference? I'll just give you a heads up. The original program is in source code. That's your source. And the object that you'll end up seeing translated is called a machine language. Do you understand? And then we have compilers, now we have linkers. some programs we use are already compiled. The object code is available for us to use, for example, input and output. So sometimes you'll just see the computer. You don't really see the background code operating. You just switch on your computer. When you switch on that computer, you don't see that the code is running on an operating system. It's doing tests. It's doing hardware diagnostic tests that, okay, when the computer is fully functioned, all the hardware is in place, everything is going according to plan, run. You don't see that code being implemented on your screen as output. It's running in the background. Those are routines that are already there. So the compiler has already compiled it and it's linking it to the certain objects and it's running, and then you end up seeing a result. So what's the responsibility of a linker? A linker combines the object code for the program we write and the object code for the pre-compiled routines into the machine language program the CPU can run. Basically what I mean here, again, I'm going to emphasize, the object code was the code that, let's say you're using Apple, the code that they put in the manufacturer, that for you to see the computer going on, the program needs to run this in the background. That object code is translated into routines. Like, let me say, for example, you take out the RAM. RAM is random access memory. If you take out the RAM in the computer knows that if you switch on the computer and the RAM is not compatible or is not there, it will send out an error message telling you that I'm not okay, I cannot start, you have failed the test for everything to go well, so therefore I cannot start. You see? And then if everything goes well, you don't see the object code that sets out all of that thing, that inspects everything. You see, you just see routines. You'll see that, no, the computer is giving me an error. I don't know what happened. It's giving me an error. The error is a compiled routine. They have made allocation for that error message to appear to you, to signal to other people who are technicians that this is what's wrong with this machine. It doesn't just keep quiet. It has a way. And if it's quiet completely, we know that it's a different type of error. It's maybe a motherboard, because the motherboard is the one that the code runs on. And then machine language is a program the CPU can run. We've already covered that previously. So conclusion to this lecture, a continuation from yesterday's one, is, can you list the 5 main components of a computer? Describe the work of a computer. What does the computer do based on all of these things that I've explained? And then you can comment on the status. You can comment on the YouTube place, and then let's just interact. So now we're getting into problem solving. I love that because I love solving problems. That's why the company's name is Solutions, Work Solutions. I love solving problems. Algorithm. I'm sure you've heard of it. There's such an algorithm, and computer scientists and computer science students sound fancy when they say, no, that's an algorithm, and it just passes over your head. You don't understand what they meant. It's very simple. It's a sequence of precise instructions that leads to a solution. What does that mean in simple terms? Precise instructions. Certain instructions that are precise. I want to find another word that's simple for precise. Designated, specific instructions that leads to a solution. So, for example, if I'm typing something and I want to print it out, there's designated instructions that once you press Control P or print, it goes straight to the printer. It gives you that access to the printer, and then it will even show you which printer. It doesn't go to something else. It's precise. So that's an algorithm. When you're logging in and you've put in your details and you press login, it doesn't take you to another person's page or anything. It goes straight to where the instructions have been instructed to go. You see what I mean? That's an algorithm. You can Another example that's day to day is YouTube. When you're playing music and all of that, you can't type Beyonce and then something comes up. When you've put in that name, it'll go straight there. So that's an algorithm, and then it'll give you suggestions of even other music of Beyonce. That's an algorithm that says if a person chooses this name, even suggest other things for them. So that's an algorithm. And sometimes you will see that if you watch certain content, when you come up again on YouTube, you will see that similar content coming up as suggestions. Those are algorithms that are running in the background that make your experience more nice for what you are doing, so that your the things you like are grouped. So then that's an algorithm. A program is an algorithm expressed in a language the computer can understand. That's a program. So you'll just see it as a program coming up, but it's algorithms inside. And what are algorithms? You'll answer that. Program design. I love this. This is where most students fail. This is where most students decide to give up when we're studying in university. This is where they say no, this is too much. Let's say a class is full of 100 students. That module, 80% is coming out, because this is the place where you have to conceptualize and design the solution. You have to set out. Remember, every computer has what is instruction based, and like I said, algorithms are precise. So you have to design all of these things. So from the design, you can see if your brain is wired to become a programmer or not. You can't create a program without the design stage. You can't create a house without the design. We'll know that this person is an architect with their plan. You see, so this is the part that really people drop out in. Programming is a creative process. No complete set of rules for creating a program. There is no complete set of rules. That's why there's many languages, and that's why there are hackers. There are people who are ethical hackers that they don't go by the rules. They break the rules. That's why there's all of these. It's a total big world. So there's no rules in doing that. The program design process has different phases, two namely. The first one is problem solving phase, where result is an algorithm that solves the problem. You've put it on paper, you've written out the design. Okay, this is what I would like to do. I would like for the computer I'm going to give you an example again about the print. I want this computer to print out something. So on paper, you're going to write the